So in our notes here, we have a definition for a smooth curve, and the terminology is not so important, but I want to highlight what these derivatives mean. So if we have a parametrically defined equation, so we're doing two-dimensional, x is f of t, y is g of t, and it says each function independently is continuous and differentiable, and then it says if both dx over dt and dy over dt are both continuous and never simultaneously zero, then we have a smooth curve. Okay, so what does that mean? Let's look at dx over dt and dy over dt. So dx over dt means we are only looking at the rate of change of this over time. dy over dt means we would only be looking at the rate of change of this over time. So I could be asked about dx over dt or dy over dt, and those are derivative functions in terms of t, but they would only be telling me about a horizontal or a vertical rate of change over time, okay? Which, if we think about this curve, okay, so ignore the left and right and imagine that I'm just, as t increases, I'm just looking at y. So I would have -3, and then I would be going up, okay, -3, -1, 1, 3, 5, etc. Or if we would have started down here at the -5. Okay, so dy over dt is never changing. It's just a 2. Dx over dt, though, does, because if we think horizontally, we start over here at -6, and then we're at, let's see, where'd we go next? I'm sorry, +6. +6, and then we're at 2, and then we're going down to 0, and we get to -1/4, and then we, well, okay. My pen wants to draw a line. And then we start coming back, okay? And then we end up over here. So there is a time when dx over dt is equal to 0, and that is at x equals -1/4, okay? Or when t is equal to -1/2. So independently, those things can be asked. And there might be, like I said, you may have questions about just those, but let's talk about dy over dx, because if something is talking about the slope of a curve, we are looking at dy over dx. We're looking at the rate of change of y with respect to x. So we want dy over dx, but this will be in terms of t, because the functions are defined in terms of t. Yes, we do have a process to eliminate the parameter and write it as dy, or in terms of like y is a function of x or x is a function of y, but that is not always practical, and it is not always what's requested. So let's think about what this means. This means that we are if we want dy over dx, we are going to take the derivative of the y function, which is given in terms of t, so dy over dt, over the derivative of the x function, which is given in terms of t, so therefore with respect to t. Or in other words, this is going to be, let's see, we're up here where we're using f of t and g of t. I'll rewrite those variables. Excuse me. So if, x equals f of t and y equals g of t. All right, so this is the same as g prime of t over f prime of t. Okay, so in other words, if I want dy over dx, but it will be in terms of t, like the variable will be a t, I need to do the derivative of the y function with a variable t over the derivative of the x function with a variable t. Okay, that one is pretty straightforward. Let's think about applications of that. Horizontal and vertical tangent lines. If the numerator, so g prime, is equal to 0, but the denominator is not, then we have a horizontal tangent, and at a place where dx over dt, the denominator is equal to 0, but the numerator is not, then we have a vertical tangent line. Okay, so that should make sense with what we already know about derivatives. Okay, here's the part that can get us a little bit turned around, but I promise is not that bad. So for the second derivative, we want, we want the derivative of dy over dx, which is in terms of t, and we want this derivative with respect to t as well. WRT means with respect to. Okay, so also in terms of t. All right, so we want d squared y over dx squared. This should look familiar. This is not new, okay? So this means we are taking the derivative with respect to something of the first derivative. And if you're thinking, what's that something? Well, if I want this to be d squared y over dx squared, I need an x here. Okay, and I'm taking the derivative of the first derivative, which I already know to be dy over dt over dx over dt. Okay, so I'm taking the derivative with respect to x of that. Here's the issue though. This is not written in terms of x, it's written in terms of t. So how do we handle that? We're actually taking the derivative with respect to t of this and dividing by dx over dt. So this is the derivative with respect to t of my first derivative. And again, this is in terms of t. But I have to divide by another dx over dt. And this right here is the thing that trips students up, that we forget. Yes, we're taking the derivative of an expression that's in terms of t, and our derivative is in terms of t, but we have to divide by another dx over dt. And then that process would repeat if I needed the third derivative or the fourth. I would keep taking the derivative of whatever I have and dividing by dx over dt every time. So let's do an example of that. Okay, so find the first and second derivative of this parametrically defined curve. X is given as 5 secant t, y is given as 3 tangent t. All right, so first derivative, it's a little bit bigger. My first derivative is going to be dy over dx, okay? And I know that this is the derivative of the y function, 3 tangent t, over the derivative of the x function, 5 secant t. Okay, and because I remember my derivatives, this is going to be 3 secant squared t over derivative of x, which is 5 secant t tangent t, and I do want to reduce that. I can reduce everything by secant. I'm going to leave the 3/5 in front as a coefficient. That will make my second derivative easier. And then I have secant t over tangent t, which, because I know trig identities, I also realized that this will reduce. This is 1 over cosine. Down here, this would be cosine over sine. So it reduces to a sine in the denominator, which is cosecant t. That's going to save me effort on my second derivative if I don't have to use the quotient rule. Okay, so pay attention to the trig stuff to see what can be simplified. All right, so this is my first derivative. And then if I want to evaluate, so let's say at t equals pi over 6, okay, then I'm just plugging pi over 6 into this, so I get 3/5 times cosecant of pi over 6, which sine of pi over 6 is 1/2, so this is 2. So 6 over 5 is my first derivative at t equals pi over 6. Okay, and then for the second derivative, I'm going to take the derivative of this with respect to t divided by another dx over dt. So the derivative with respect to t of 3/5 cosecant t divided by dx over dt. You don't need to write this in between step, but this is new, so we're writing out what we're doing, so it makes sense. Okay, so then the derivative of this, let's leave the 3/5 in front, and derivative of cosecant is negative, I'm using parentheses so it doesn't look like I'm subtracting, negative cosecant t times cotangent t over another dx over dt. So back to this, its derivative is 5 secant t tangent t. Okay, and then we can do a little bit of simplifying here. Coefficient will be negative 3 over 25. What do I have? A cotangent over a tangent. That's going to put a tangent. Let's do this. Let's move the tangent up and give it another cotangent. Cosecant over secant is another cotangent. So this, and then this coming up make cotangent cubed of t. That was trig stuff, not calculus stuff. If something there threw you off, write everything in terms of sine and cosine and look at what simplifies. Okay, and then we're going to say at t equals pi over 6, that's equal to negative 3/25. Cotangent of, well, cotangent cubed. Cotangent of pi over 6 is 1 over tangent of pi over 6, which is 1 over root 3. So root 3 cubed is my answer, or I can simplify that as negative 3 to the 5 halves. Let's see, over 25. Okay, and there, or you could write it as negative 9 root 3 if you wanted to. Okay. Lastly, here we have an application of this. Let's see. So find the slope of the tangent line to the curve. Okay, so curve is given x of t, y of t, and I don't know what x and y are, but I do know what their derivatives are. So the slope of the tangent line is dy over dx, which is arc sine e to the negative t squared over natural log of t plus 1 at, really I should have put this in here, at 2, 5. Or we can say, actually I don't even need that part. It's not 2, 5 because it's in terms of t. So I'm going to say at t equals 1. Darn. Okay, which comes out to be, let's plug this into a calculator, comes out to be about 0.544. And here for the x-coordinate of the position, so this is only asking for the x-coordinate, AP's favorite formula says we can start with a known position and then accumulate the rate of change to get an after position. So this is just from the second fundamental theorem. It just happens to be with parametric functions. So x of 3 is going to be x of 1, the known value, plus the integral from 1 to 3 of x prime of t, or dx over dt, if you want to use that notation. This is a 2, and so I get 2 plus 2.159 approximately, which is 4.159.